Now I would like to invite Mr. Deveci for his presentation. Please.
First of all, I would like to take this opportunity to thank all who contributed to this event, particularly Professor Haci and our sponsors, and my colleagues and staff and students. Now I'm going to present bio-oxidation of refractory gold ores. The talk will include I'm going to introduce gold ores, refractory gold ores, and their pretreatments, particular pretreatment options. And then I will move on bio-oxidation. I will give some background information on historical development of the process, industrial applications, pros and cons, and then I will provide some insight into the bio-oxidation principles, microorganisms involved, and their particular characteristics. Then bacterial action on sulfides, so what happens and how it occurs, I'll mention about it, and the chemical aspects of the bio-oxidation processes. And then move on to bio-oxidation practice currently, and I will finish off with future trend. Gold ores, from metallurgical point, we classify gold ores as free milling ores and refractory ores. Free milling ores, they are easy to beneficiate and quite easy to and respond well to direct cyanidation, which means in cyanide leaching after suitable pretreatment, physical pretreatment, like grinding down to 75 micron, we can get high gold recoveries. So that's why we call these particular gold ores free milling ores. And refractory ores, they are defined as those ores unacceptable low extraction of gold, which is the characteristics in their cyanide leaching. So low recoveries essentially is below 80%. And share of refractory ores are increasing, and new deposits are generally more refractory. We can see the free milling ores, they are quite coarse and easily treated by either gravity methods or direct cyanide leaching. What's the reason for refractoriness? There are two reasons, which is one of them is the physical encapsulation of the gold within sulfides, and particularly gold is in submicroscopic particles and within the sulfide matrix. And particularly like arsenopyrite, pyrite, and pyrrhotite are the main gold-bearing phases, and they can contain much gold. Another reason for refractoriness is the chemical interference by any of the ore constituents, like it could be a carbonaceous content or copper in particular, or another components of the ore. These components may lead to high cyanide consumption or oxygen consumption in case of pyrrhotite, and carbonaceous ores, which are known as pre-rubbing ores, they absorb the gold as soon as solubilized in cyanide solutions. That's why they lead to low gold recoveries. When we look at the treatment of refractory gold ores, free milling ores, they are particularly easy to treat, and after only size reduction, more than 90% of the gold can be easily extracted in cyanide leaching. However, for the refractory ores, because ore encapsulated in pyrite or arsenopyrite or pyrrhotite needs to contact with cyanide solutions to dissolve. That's why they need the first chemical pretreatment to open up or destroy the sulfide matrix so that it can be exposed to the action of cyanide. And there are many methods for refractory ores. One of them is biooxidation. Biooxidation is an alternative pretreatment process to traditional roasting and recent pressure oxidation. So it is essentially an oxidation process with the involvement of acidophilic bacteria to decompose the sulfide matrix so that expose the gold to the action of cyanide in something cyanidation stage. And we use the microbes to destroy or to aid the destruction of sulfide. When we look at the historical background, essentially isolation of bacteria dates back to 1950s, and Coleman and Hinkle isolated the bacterium as Tyrosus pyroxylus in 1950s. Then a lot of research will get into the bio processes, but particularly biooxidation of refractory gold ores started around the 1970s. And in 1984, pilot test and pilot plant was established in South Africa at Fairham plant and operated 10 tons per day rate. And commercialization of biox processes essentially in 1988, thereafter 88, and after 1990s, there are many biox plants built up around the world. Those are known as biox process, Biox process, and Russian process, Biolox process. Those are the scenes from the bioxidation plants all over the world. When we look at the plants, there are about more than 10 plants currently operating around the world. Not in the list, there's one in Olympiada plant in Siberia, Russia, using their technology Biolox process. And there are also other processes as well. Biox plants in operation in 2009 with a total capacity of 4,500 per day. And the gold production from biox operations for 2000 is estimated to be around 47 tons of gold. Why biooxidation? It is a relatively low capital cost process, and operating costs are also competitive. Reduced environmental impact, there is no SOx emissions, SO2 emissions to the atmosphere, as well as no toxic components like arsenic gases as well. So atmospheric conditions are used with the ease of operation. Its operation is simple, and because it is operated at atmospheric conditions, so it's easy to control as well. So high gold recoveries is one of the main advantages of biooxidation process compared to the roasting in particular, and it is also suitable for small-scale applications, in particular remote areas. This is one of the most important advantages of biooxidation process. There are, of course, disadvantages of the process. The main disadvantage is the slowness of the reactions, which may take days, up to 4 to 6 days, compared with the pressure oxidation or roasting takes within hours. And low pulp density, another disadvantage of these processes, which is limited to around 20% by weight. and low metal resistance of bacteria. In other words, metals at certain concentrations are toxic to these microorganisms, which affect their performance as well. One of the main disadvantages of this process is also high cyanide consumption compared to the alternatives, particularly roasting and pressure oxidation. And the bio-oxidation is sensitive to process interruptions. Recovery from the interruptions is a little bit difficult. I'm going to bio-oxidation, just to give some terminology. We use bio-leaching and bio-oxidation in terms interchangeably. They are actually synonymous, but there's a subtle difference between them. So bio-oxidation often refers to the oxidative pretreatment of refractory gold ores, so it is used as a pretreatment process known as termed as bio-oxidation. On the other hand, bio-leaching refers to the extraction of metal directly from ores, concentrates, or another waste as well. You can see, so bio-oxidation in the case of refractory gold ores used as a pretreatment process. However, in the extraction of, for example, copper, used as the principal means of extraction method for copper. So, bio-oxidation, there are two aspects. One is biological aspects and chemical aspects. In other words, there are entities within the system. These are bacteria, and bacteria wants to grow under suitable conditions of temperature, air, and pH and pH. So they produce metabolic products, which are essentially the leaching agents, and we use them in the leaching or oxidation of the mineral. So, bio-oxidation is based on the exploitation of acidophilic bacteria to oxidize gold-bearing sulfides like pyrite, arsenopyrite, and pyrrhotite. Acidophilic bacteria means they grow under acidic conditions of like pH 1 to about 4.5. And these are chemonosotrophic bacteria, which means derive energy required for their growth and other metabolic functions from the oxidation of substrate like ferrous iron, elemental sulfur, and reduced sulfur compounds, which is the main properties of these microorganisms that we utilize in the bio-oxidation. So they are aerophilic, which means they require oxygen, and they are autotrophic, which means they need carbon dioxide, or they fix the carbon dioxide from the atmospheric carbon dioxide. There are many microorganisms that involve in the oxidation of sulfides. Basically, we classify into three based on their operating temperature. And mesophiles, the most important mesophiles, acetylacid thyroxine, lactose thyroxines, and acetylacid thyroxines, they have characteristics like can oxidize iron or sulfur. Some can only oxidize just sulfur or iron. And moderate thermophiles, they operate over 40 degrees Celsius up to 55 degrees Celsius, and extreme thermophiles, which are active at temperature above 6 degrees Celsius. And you can see the morphological properties of some of the bio-oxidation bacteria, like Leptospirillum. They have distinct characteristics, morphological characteristics like spirillum in shape, and acetylacid thyroxines, they are like rods, and acetylacid thyroxines, similar to acetylacid thyroxines, but shorter in length, and or microorganisms. And extreme thermophiles, they are known as ACA, and they like cocoids, and they have no solid cell wall. So these microorganisms used as a consortium, in other words, used as a mixed cultures of iron and sulfur oxides in the bioxidation process. For example, in the biox process, asterosis ferroxidins, asterosis thyroxidins, and leptosperm ferroxidins, all three are used together. At temperatures, they have some properties important to bioxidation. For example, leptosperm ferroxidins and asterosis thyroxidins, they are more temperature tolerant, so they dominate the processes at 40 degrees Celsius. Other important microorganisms that dominate the microbial population are Aspergillus caudas, Leptospira ferrifluum, Sulfuribus-like bacteria, and Ferroplasma-like archaea at 45 degrees Celsius. So, what's the role of bacteria? The main characteristic of these bacteria is their ability to utilize ferrous iron, in other words, converting ferrous iron to ferric iron and elemental sulfur to sulfuric acid. And this is the primary role in the bioxidation or bioleaching processes. Because ferric iron, which is a powerful oxidant with a reduction potential of around 1.77 volts, which means only a small quantity of ferric iron is present in solution. It means it can theoretically oxidize almost all known sulfides. And in the presence of, essentially this reaction over here is a chemical reaction, but in the presence of bacteria, this reaction can be accelerated up to a million times. That's why the bacteria effect, called catalytic effect of bacteria. Here we see the action of bacteria on sulfides. They can attach themselves on the sulfide mineral, or they can be in the bulk of the solution, or both mechanisms. Some of the bacteria can attach on sulfides, or some can be in the bulk of the solution. So, oxidation of sulfides occurs indirectly by attached to the surface through the extracellular polymeric layer, or cooperatively, both in the bulk of the solution or on the surface of sulfide minerals. There have been a lot of debate over the years about the mechanism of bacterial oxidation. Some claim that the oxidation process can occur directly, which means bacteria stick to the surfaces and metabolize the mineral, but recent work showed that there is no actually the direct action of bacteria. It's purely chemical, which means the role of bacteria is the oxidation of ferrous iron to ferric iron, in other words, generation of ferric iron in the system, and ferric iron attack to the mineral. So, based on key intermediates involved, Sand et al. Proposed that bioxidation of sulfides occurs via the thiosulfide or polysulfide pathway, depending on the sulfide mineral involved. Which means minerals like pyrite, they can be oxidized directly to the sulfate through the formation of thiosulfide as the primary sulfur intermediate. On the other hand, sulfides like sphalerite or arsenopyrite, they can be oxidized within the system by ferric iron or acid attack, and they generate elemental sulfur on the mineral surface, and if there is sulfur oxides within the system, they can remove the sulfur formed on the mineral surface. So pyrite is oxidized via thiosulfide pathway, as we see here, which means when pyrite was oxidized, no elemental sulfur or just little elemental sulfur can form, and basically sulfide weight of the pyrite converts to the acid, as we see here. And ferrous iron reduced here can be converted to ferric iron by bacteria present within the system. And sulfides like sphalerite are oxidized, as shown here, in these reactions. And we see the elemental sulfur formed on the mineral surface. We see from here as well this particular ore particle was subjected to the bio-oxidation, and we see the accumulation of sulfur on the mineral surface. And if there is sulfur oxidized within the system, this sulfur will be removed from the surface of the mineral. Oxidation of sulfides. In the oxidation of sulfides, properties of sulfides is important. And for example, some sulfide minerals can be oxidized more easily than the others. In this respect, pyrite can be classified as null, which means it is not easily oxidized compared to sphalerite. And there is a rest potential for each sulfide, which means the oxidation conditions should be more positive than these potentials to effectively oxidize these minerals. In this regard, redox potential of the system is of prime importance for controlling the oxidation of sulfides. And in bio-oxidation systems, redox potential depends on the ferric to ferrous ratio. And of course, we can infer from this table that the galvanic interactions also contribute to the oxidation of sulfide minerals present, which means, for example, when pyrite and sphalerite are present within the system, pyrite will be catalytically protected, while sphalerite will be analytically oxidized. As we can see from the figures here, this is before the leaching, and this is after the leaching, when we see the pyrite is more difficult to oxidize compared with the sphalerite. And we can see that when sphalerite was oxidized, elemental sulfur will form on the mineral surface. But pyrite has no elemental sulfur formation, which means that it oxidized through thiosulfide mechanism. This provides a support for these clamps. And we can see here the oxidation of pyrite. We can take this one as the iron profile. The oxidation of pyrite will only occur after certain redox potential, which is about 550 millivolts. But sphalerite can be easily oxidized beforehand. So when we look at bio-oxidation practice, it is a method, suitable method for the refractory bubblers, or treated by physical pretreatment methods like pressure and grinding, and then floated to obtain a flotation concentrate. Here, this flotation involves the flotation of actually pyrite and arsenopyrite as they bear phases. This, at this stage, because these chemical pretreatment methods incur a cost, so to reduce the cost, bulk of the material can be reduced by flotation or selectively recover gold. Then the bioxidation is applied, and after the oxidation of the sulfide, then the gold remains in the solids, and after solid separation, the solid fraction is sent to cyanide leaching. You can see here, here is the biox plant, which is bioxidation is carried out by 6 reactors, which have equal volumes, and 3 of them placed in the first stage, and one in parallel because allows the build up of bacteria, in other words, to prevent the washout of bacterial organisms from the system. And afterwards, counter-current decantation is used to wash the solid fraction, and the overflow from counter-current decantation, which contains arsenic, iron, and other metals, and which are subjected to the neutralization in 6 reactors here to precipitate arsenic and iron as well as other metals. And the solid fraction is subjected to cyanide leaching. We can see the reactions over here, and these reactions are important because some of them produce acid, and some of them consume acid. That's why the composition of the concentrate is of prime importance. In this regard, oxidation of pyrite produces acid, which means if there are more pyrite in the system, so after oxidation it will acidify the medium, so the neutralization may be required. And also pyrite is more difficult to oxidize, so if the pyrite is the main gold-bearing phase, then this may lead to the extension of residence time, because more time is required for the oxidation of pyrite. There are also secondary reactions within the system. For example, arsenic can be precipitated during the process as ferric arsenate, and which is undesired reaction. Some geoside, or in other words iron precipitates, may form, but they are actually unwanted or undesired reactions, and the formation can be controlled by good control of pH. Because the oxidation of sulfides are exothermic reactions, so cooling is required because bacteria can only thrive at certain temperatures. For example, mesophilic bacteria is often used, and they can tolerate temperatures up to 40 to 45 degrees. So to control the temperature, cooling is often required. And there are aerophilic and autotrophic bacteria, and which means continuous supply of oxygen and carbon dioxide from the air is essential for a good operation, but solubility of oxygen is often limited. A minimum dissolved oxygen concentration of 2 milligrams per liter should be maintained for an effective oxidation process. You see, at a certain point, the maintenance of oxygen at a certain level, which is essential. And here we see the decrease in the solubility of oxygen when temperature is increased. The addition of nutrient salts is required to support the growth of bacterial population, nutrients in the form of salts like ammonium salts, potassium salts, and phosphorus salts are added to support the bacterial growth. Hot density is limited around 20%. The main reason for this limitation is the availability of oxygen or the transfer rate of oxygen to the system. And to increase the oxygen rate, we need to increase the mixing rate. When you increase the mixing rate, it adversely affects the bacterial viability. It means you start killing the bacteria. So, in some cases, only partial oxidation of sulfides may be required for good gold recoveries in subsequent cyanidation. And we see from here, most often you don't need to oxidize all the sulfides. And bacteria has limited tolerance to arsenic 3 compared to arsenic 5. That's why good oxidizing conditions should be maintained within the system. Limestone is used for the first stage of neutralization, which is carried out in two stages. In the first stage, the pH is increased to pH 4 or 5 to precipitate arsenic as ferric arsenate. And for this reaction to be effective, the ferric to arsenic ratio is important and should be maintained more than 3 for a stable arsenic precipitates. In the second stage, lime is used to increase the pH to pH 7 and 8. And air is continuously spotted, as you see here, the circuit. And future developments, one of the main disadvantages of the biooxidation process is the cyanide consumption during the cyanide leaching. The main cause of this is the partial oxidation of sulfides, so they lead to the formation of thiocyanide in particular, and the iron precipitates, they also quite easily dissolve in the system and consume cyanide. So in recent years, many work on this issue having carried out. And power input is one of the most important operating costs. So in recent years, more effective mixing systems like impellers, hydrofoil impellers, in particular axial impellers. They are work on the development of these impellers to improve the gas transfer, oxygen transfer to the system, as well as to reduce the power input of these impellers. The application of a combination of mesophiles and thermophiles in biooxidation is seriously constant issues. The main reason for this is the cooling requirements for the mesophilic systems, since the oxidation of sulfides is an exothermic reaction, so the heat evolved can be benefited actually if you use thermophiles. And another reason for this surge is the complete oxidation of sulfides, so that it can be used as a means to reduce the cyanide consumption in cyanidation stage. And also some work to develop an understanding and control of bacterial population, so that the more affected bacteria can be found or manipulated, so that the residence time, for example, may be even reduced. And heat biooxidation will probably be the future developments in this area. And that's all I was going to say. Thank you.
Any questions?
Please.
I would like to ask, what is the effect of cut-off grade optimization in refractory gold deposits, sulfide type deposits, and the plant capacity, the mill capacity, does they affect the recovery, the treatment recovery in refractory type deposits, gold or metal deposits?
It is, next cut-off grade depends on the gold price. I don't know, it's quite volatile at the moment. It went up, so I'm sure it went down. But to get an idea, for example, like 2 to 3 gram per ton, for example, it can be used as a base for example, the agitated tongue bleaching, that below 2 to 3 grams may be used for heat bleaching operations. And I think the last figure I've seen was around 1.7 gram per ton. I'm sure the operators will answer or will give more real answers anyway. And for your second question, plant capacity, which is really important. The main characteristic of bio-oxidation is the suitability for small-scale operations. And when compared to the alternatives like pressure oxidation, which is capital intensive, so it is suitable for high capacity operations like over 1,000 ton per day. And below 1,000 per day, operations by oxidation will be more economic, you can say. Of course, it depends on other factors anyway. Please.
Just want to ask you comments about the neutralization of the acid and the precipitation of the ferrous sulfate. So this will add to the cost of the operation?
Yes, of course, it is, because it's the method of disposal of the waste. And in neutralization stage, because in the solution there are ferrite, ferrous iron, and arsenic, as well as other metals as well, like zinc and copper. And in the neutralization stage, ferric iron is precipitated as ferric arsenate, which is quite, or at least is claimed to be stable. And to remove the ferrous iron, the air is injected to convert the ferrous iron to ferric iron and precipitate as ferric hydroxide. Elbette.
Hocam teşekkür ediyoruz. Benim takıldığım bir tek var. Şimdi bu Yazıcı prosesi dünyada terk edilmiş bir proses. 2000'li yıllardan sonra bunun deponi problemleri var. Özellikle çevre kirliliği çok yaratıldığı için bizim çinko hidrometallurjisinde çok biliyorsunuz başvurular, hoca da anlattı. O bütünlük çarpıklığının değerlendirilmesinde Yazıcı prosesinden vazgeçildi. Yani bu şekilde bir de benim merak ettiğim bir şey var. Şimdi siz arsonopiniki biyobakteri biyohiçiyle açarken, refrakter yani non-refrakter cevherine getirirken arsenin çözeltiye geçişi artı 3 değerlikli mi oluyor, artı 5 değerlikli mi oluyor?
Evet, ilk sorunuzdan başlayayım. Esasen burada jeoloji prosesi uygulanmıyor. Jeoloji ortamda lityum ilave ediyoruz. Bir de cevherde örneğin kirler vesaireden gelen potasyumdur, sodyumdur. Bunlarla beraber ortam uygun olduğu için çökeliyor. Biz aslında onun çökelmesini istemiyoruz.
Doğal oluşuyor.
doğal olarak çökeliyor. O istemediğimiz bir durum esasen. Hani burada jeolojik olarak çökeliyor ama biz çökelmesini istemiyoruz. Bunun da temel sebeplerinden bir tanesi siyanür biçi esnasında siyanür tüketimine etkilen önemli parametrelerden bir tanesi. Demir çökelekleri. Yani burada istemeden gerçekleşiyor. Tabii koşullar uygun olduğu için o şekilde gerçekleşiyor. İkinci sorumuzda esasen arsenik çözüldüğü zaman artık şeklinde ortama geçiyor. Ancak ortamda ferrikleri var, yani oksidatif koşullar. Dolayısıyla arsenik 5'e oksitleniyor. Bundan örneğin ortamda bulunan pirit özellikle katartik rol oynuyor. Bu şekilde buradakiler size gösterdikleri genel reaksiyonlar. Yani esas olarak söylediğiniz gibi arsenik 3 şeklinde çözülüyor ama işte ferrik levreler arsenik 5'e oksitleniyor. Ondan sonra zaten çökeliyor.
Hocam bir soru daha sorayım. Şimdi siz sunumumuzda dediniz ki asıl işi yapan demir artık çöküyorlar.
Evet.
Peki biz bunun yerine bakteri kullanacağımıza niye ferrik güç yapmıyoruz? Yani demir artı gücü bu sisteme niye direkt yapıyoruz?
Evet, hemen ona da cevap vereyim. Çünkü sistemler şöyle konsantre düşünecek olursak kullanacağım ferrik sülfatın çözünürlüğü sınırlı. Dolayısıyla çok fazla miktarda ne kullanmamız gerekiyor? Ferrik kullanmamız gerekiyor ki bir ara hesaplamıştım, şu anda hatırlamıyorum. Çok fazla ferrik demire ihtiyacımız var. Yani o kadar ferrik demiri ortamda çözemeyiz. Birinci sebep bu. En önemli sebeplerinden bir tanesi bu. İkincisi, kimyasal oksiteyiciler kullanabiliriz ama onlar da pahalı. Ve en önemli sebep de zaten pirit, sülfürlü minerallerde veya burada sülfürlü cevherlerde veya konsantrelerde veya burada olduğu gibi refraktör cevherin kendisinde zaten ortamda mevcut. Yani ekstradan bir şey yok. Dolayısıyla bakteriler ortamda olduğu zaman sürekli olarak ne yapıyor? Ferrostemde ferrik devre oksitliyor. Ferrik devre indirgendiği zaman tekrar bakteriler. Yani liç reaktifini ortamda tekrar rejenere ediyoruz. En önemli avantajı o. Bu özelliklerinden esasında.
Teşekkür ederim.
So, thank you, Dr. Deveci. Now we have 20 minutes coffee break. Please enjoy.
Burada